A circuit consists of battery A with EMF 60 volts and internal resistance 2 ohms. Then battery B with EMF of 12 volts, that's this guy over here, and internal resistance 1 ohm, 5 resistors as shown in the diagram. The first thing we're asked to calculate is the current in the 8 ohm resistor. So we'd be interested in the I through that guy. I've gone ahead and taken the liberty of writing out some successively simplified diagrams. All I want you to notice about this one is that I got this 1.14 ohm resistor by calculating these in parallel. See for yourself if 1 over 8 plus 1 over 4 plus 1 over 2 to the negative first power is indeed 1.14 ohms, and check in later for a more detailed video on how you calculate the equivalent resistance of a chunk of resistors in parallel as such. But that value is 1.14. I've then gone ahead and taken the liberty of writing a still more simplified version of the circuit, where I've wrapped up these two resistors in series by adding them linearly and arriving at 3.14 ohms for the most simple version of the circuit that we could possibly get. The next thing I'm going to do is try and figure out the current in the whole circuit. This is one of those situations where there's more than one source of potential. So it would be prudent to apply Kirchhoff's loop rule. Say I decided to start here at what I'll call point A, and here at what I'll call point B, and travel along my loop. The first thing you might see is that I start at the positive end of a battery with an EMF of 40 volts. So the Kirchhoff's loop law statement, which states that all the voltages in such a loop as this one would add to 0, has me starting with point A with 40 volts. Traveling through the circuit, the first thing I encounter is a 3 ohm resistor. That would cause my voltage to drop in accordance with Ohm's law, V equals IR, by I times that resistance 3. Remember, I don't know this I yet. The next thing I encounter is the positive end of another battery. Now going from the positive end to the negative end along the direction that I've chosen would be a voltage drop. If it was turned around, it would be a gain of 12 volts, but in this case I'm going to have to subtract 12 volts. Continuing to travel along my circuit, the next thing of interest that I find is this 3.14 ohm resistor. I will have to drop a voltage equal to I times 3.14 before finally encountering nothing of interest until I reach the negative end of the battery I started with. At this point, the voltage statement should sum to 0. I will spare you some of the menial math, and instead again take the liberty of showing the solved version of this equation, which tells us the very value of the current, 4.56 amps, going in this direction the way we have drawn it. At this point, it's helpful to know that going back up a layer to a slightly more complex circuit, we have again 4.56 amps going around this entire loop. And since all of these elements are in series, that goes for this, and it goes for this as well. This is my resistor of interest at the moment, because inside this composite resistor with value 1.14 ohms is the 8 ohm resistor, actually in parallel with two others. So being able to say that the current through here is 1.14 ohms is helpful, because now I could calculate the voltage through this resistor. The voltage through my 1.14 ohm composite resistor is equal to the current through there times the composite resistance. So 1.14 ohms times 4.56 amps. We find that the voltage drop through here is about 5.2 volts. Now that's helpful for answering question A. Let's get it within the view here. That's helpful for answering question A, Because, of course, through parallel elements, the voltage drop must be the same through every single element. And indeed, the same as the very 5.2 volts we calculated through the composite element represented by these three. So to go from here to here is a voltage drop of 5.2 volts. That's enough information to conclude what the current in the 8 ohm resistor is, since, by Ohm's law, current is equal to V divided by R. I'll take my 5.2 volts and divide it by 8 ohms, being able to conclude that the current through the 8 ohm resistor is 0.65 amps. Next, we can find the power dissipated in the 4 ohm resistor pretty easily as well. One of the definitions of power is V squared over R. Since the voltage through the 4 ohm resistor should be the same as the voltage through the 8 ohm, I'll apply the 5.2 volts as being voltage through the 4 ohm and the resistance of 4. 5.2 squared divided by 4. Off screen I have my calculator. 6.76 watts. Finally, we get to calculate the terminal voltage of battery A. That's this guy. Okay? So terminal voltage we usually expect to be a little bit less than the 40 volts posted because there is some internal resistance here. If I take a small, we kind of make a little diagram. I'll make some room for it. It'll be worth it. Just move some of this stuff down somewhat. If I were to draw a more detailed diagram of battery A, it might look something like this. We have a tiny resistance A equal to 2 ohm, and the sort of EMF generating element EA equals 40 volts. Now that is all sort of inside the box representing the real life battery, and that would be something like that if I were to go in detail somewhat. Well, as we know, the current through the whole circuit, as we calculated, is I equals, what was it? Oh yeah, 4.56 amps. Now the voltage drop, so to speak, if I were to follow the current from here to here, would first be equal to negative I times the internal resistance. But then I would go in the negative end of my EMF generating element and out the positive end, which would correspond with a rise of 40 volts. If I plug everything in, I should get negative 4.56 times my internal resistance of 2 plus 40, and find that the voltage dropped from here to here, or the terminal voltage, VT. 1 second while I run this through my calculator. Be slightly lower, albeit definitely significant if we're talking real batteries, 30.88 volts for a terminal voltage. Now this idea of the current being known and traveling through the resistance, dropping, and then gaining through the EMF generating element, that gives rise to the formula VT equals EMF minus IR. That is generally going to be true for terminal voltage of batteries. But conceptually, it's good to know that it sort of comes through an application of current, what it does, how it drops through some elements, resistors, and rises from the negative to positive ends of our EMF element.